approximately, then we may have the maximum intrinsic information. But then, is that what we want? Yeah, somehow. If you can equally distribute the sample using this attribute, then maybe, just maybe, the way you make the tree can be better, because now there is no phenomenon like there is a branch with very little number of sample, and the author consume almost every sample in the original set. That's no good, right? So this kind of intrinsic information is also a criteria that you want to have. Now, but it biased toward something. And now you see that even though the intrinsic information is biased a little bit, it's still not perfect. So people again propose some idea like, all right, if you base on the gain information only, you may encounter some issues like the bias in multivariable attribute. And if you favor intrinsic information, you need bias, but then you lose the advantage of that gain information. In other words, we try to make the subset to be pure. So they propose, let attribute A that somehow balance between the gain and intrinsic, right? We want to maximize the gain, but we also want to maximize the intrinsic. So let's just define this kind of ratio, and we call it gain ratio. Okay, and using this for select the attribute A, and of course you are going to maximize this one as well. Given that fact, should we rely on this one? I don't know. This is a very tough questions, because as the way you are looking at, all the proposal we have here are just heuristic, and because they are heuristic, no one can prove if this is good or bad. It depends on the situations, and yeah, maybe in most of case the gain measurement is accurate. In some other case, may you rely on the gain ratio. And so that is why when you use some framework like sklearn and someone saying, they will give you some note on their items. So like what kind of criteria they use to implement their items. Okay. And you have to be aware of that thing. It's very important. Then given that gain and all kind of entropy thing, you see that the calculation is quite heavy. Computational cost is high because, I'm sorry, because you are taking the log functions. So in order to reduce the complexity of the calculations, they propose another measure we call Gini. And Gini index can be computed very simple. It's just 1 minus of square pi. Well, that surprisingly effective, because now you only subtract and multiply thing, and that would rate when you have entropy the weight sum of Gini of subset, and you can have Gini as a, just like what you see in the formula. And it's similar to the thing we discussed earlier using entropy. It's quite similar. And here is the plot of Gini index and entropy. As you can see, the Gini index and the entropy are pretty much similar. in terms of the curve it provides. And so we want that, right? Compute simple, but also have some sort of same characteristic. All right, and let's see what I have here. All right, that's all about ID3, but the ID3 is not the one you want in it, because if you apply ID3 in the industry in practice, you will encounter a lot of issues. Well, some issues that I list here in the material, as you can see, is very important. First, the numeric attribute is so important. I don't know how much important I can uh, tell you, but the thing is, you see that every data you have nowadays, it's just number. You cannot classify them or discretize them into some discrete value, right? Look at them. Like they have, you go to the hospital, measure something like blood pressure, measure the sugar, Hg plus, and some other attribute. All of them are numbers. And how will you discretize this value? There's no way, right? So we have to think about it to find a way to apply the decision tree on this numeric values. The second issues you may encounter with the classic uh, decision tree is that missing value. Well, this is somehow a big deal because look at decision tree. If you have some missing value in your data, if you go to the hospital and you didn't check every possible number in the test, then how will you make the decisions? Still, the doctors still make decisions for you because they have experience, right? Now you build the algorithm for machine, and if you miss some information, but you still make the decision. That's what we are talking about. So, uh, your decision tree must allow those missing value somehow. And the third problem is the noise. Well, as I mentioned earlier, every algorithms, when they deal with the data, they must assume that the data has noise, right? And the decision tree, if you train it, most of case, your decision tree overfit with the data, and it means you overfit with the noise, and that's no good. So be careful with that. And last but not least, your decision tree should be able to approximate some concept description. Well, this is just a principle, okay? Not really what you have in practice, just a principle. But let's see where it goes. Right now, we don't really concern about that concept description. Well, what I'm trying to tell you is a concept description is like a way you read that decision tree. Sometimes you can read it into the rules, sometimes it's not. So this is a little bit our context. Now, first, let's talk about numeric values that you have in decision tree. And if last time we talked about this, then I can skip. But did we talk about this one? Not yet?
Yes, yes. No, 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 sir. No, sir.
Okay,
You did not talk yet.
I'm sorry. Did we talk about this? Not yet? Okay, thank you. So I just want to confirm because I remember we didn't talk about this one. Okay, anyway, you have some numbers, right? And you have to divide your set, original set F, into some subset based on this attribute, but this attribute contain a number. So you may not discretize this number, but to split them in some sense, right? You can either choose to split them into two parts, one smaller than theta, and the other side is larger than theta. This is like you are making a binary tree, and very often we call this binary split, right? You try to find theta A. You are looking for this theta A to split the set into two parts. Well, this is a hard problem because now you are doing two things at the same time. You have to select that theta to split the attribute A, but also you have to specify if you should choose A or not. So again, the gain of SA will be the maximum of gain S A and theta A. Just goes like this. Gain of S A equal to max over theta of gain S A and theta. Something like that, right? And so because of this, if you enable numeric values in your attribute, you have to pay attention because this requires a lot of computation in order to find theta first. And select theta already hard, but then you also have to specify if you are going to choose A or not. So that's another issue. But anyway, this is still a very good idea to select some numeric values in your decision tree, right? All right. Select the best split point is one possible solution for decision tree, but it requires something in computer programming. Like you have to know how to something that theta. For example, I may calculate one value here, and then I take another sample here. Let's say if I should go to the left or I should go to the right, and maybe you can select some theta A in the middle based on that direction. That's just some idea that we have in order to choose the best theta A as soon as we can get there. But yeah, it requires a lot of computation in general. And in the industry, there are some other way to do that. They will split your value into range, not necessary to be a very fine range of values, but still they will split them into part. And this one is not a common, well, there is no rule for this actually. What you are seeing here, the table you are looking at, is actually just an example. So just look at it and have some idea about how do they split your value into parts. But there's there's no formula for this one. No formula at all. So be careful with that. And let's see. There are some cases we need to make decision between the binary and multi-way split. You may learn about the binary tree and multi-way tree, right? So binary split and multi-way split are similar. So instead of finding a single threshold theta to split your tree in half, now you have to select multiple theta to split your tree into multiple parts. And this is harder. It's make your tree more complicated, and you don't exactly know how many branches should you split. So In many cases, the tree is very hard to read and it's not good for understanding. This is why we try to avoid this kind of situation. Okay. All right. So let's deal with another issues. When you have missing value, what to do? Well, for example, if you have a sample of data SI, right, and there is some missing value in the middle here, how will you do that? Now, suppose that the missing value is the value of attribute A. What can you do? They say that, all right, if I at this point put Si into the subsets S1, S2, and S3, that's fine, right? But then will it give me any informations about that data? No. And that's very dangerous because now, as you put Si into three subset, you are making three subset containing some more data. In other words, Si will be triple, right? And if Si was triple, it means that you will have some miscalculation later in the subset. So people say that's no good. Original contribution of that sample is just one. Why now the contribution of that sample is three? You don't want that. Okay. And so for this case, people tend to assign for each sample a weight. Okay. So because I don't have the attribute A in Si, how about split that Si into three parts and distribute them into subset, but the weight of that sample is just one third instead of one. And that makes sense because now the contributions of the sample is just one third. It doesn't affect much overall data in the subset, and that's a good thing. Okay. So in the industry audience, they will associate example with a weight in order to solve this kind of problems. And when some value is missing, they will follow this rule and inject a copy of that sample into subset in calculating process. Okay, calculation process. Okay, so that amount, that weight we mentioned about will affect the gain and gain ratio if you use those in the your heuristic. Okay, and next we are going to deal with a situation which you call overfitting. Well, when we have overfitting issues in the decision tree, we should make decisions. Should we uh, cut the tree so that you can have a better tree that not so overfitted? Well, this is possible to do so. Okay. Now, what to do? We call that pre-pruning, and there are so many ways to do so. One possible way to implement this to avoid overfitting is using pre-pruning. Pre-pruning means you stop early. That's it. Okay. So when you break the tree in the top-down fashion, you may decide to stop as soon as possible. So how to stop? Depends on your choice. There's no exact formula here, but in many cases, they will based on the entropy of your subset of your set. If the entropy of your set is not so high, it's very low. It's not necessary to be pure. Then, if that entropy of the set below some threshold, then you can decide, okay, that's enough. I will stop. I don't need to split this set further. Okay, and that's what we call early stopping. You allow some data with different class in a set. That's also possible. Now it's all about entropy. So saying about it, you can stop splitting when entropy drop below some values. All right, that's the first thing. Now let's talk about another techniques in decision tree that you may encounter. That's called post pruning. Post pruning means you have a tree already, but then you may want to reduce the overfitting issues by cut the tree, cut the leaf, and combine them together. So now post pruning means you make the full tree, overfit tree, and then you cut the tree from bottom up. Okay, you cut the leaf and you make the tree look prettier. That's the idea. Okay, so we try to simplify some operators on the tree, and we try to evaluate the tree every time we cut the tree. This goes like this. We have two techniques, subtree replacement and subtree raising. So first, about subtree replacement, you can observe this kind of example. Here we go. In this example, what you see is that we make a decisions based on some factor. So you are saying that okay, a company offer you a job, and then there are some condition in their contract. One say, okay, one based on the weight for the increase for the first year, the number of hours working hour per week, and health plans, conditions, statutory holidays, and so on. So look at the tree. You will see that some people say, okay, if the weight increase in the first year is lower than 2.5, I will consider the working hours. If working hours below 36 hours, it means that's a bad offer because the company looks like they don't have job for you to do, right? If the working hours is larger than 36 hours, you check the healthcare conditions. And if they provide you either full healthcare or no healthcare at all, you say they're bad. If they provide just 50% of healthcare, you say that is a good offer. All right. So overall, when you analyze the distribution of data in this branch, the one that I have in the screen circle, what you see is that most of them are bad. Only one decision is good. And if you look at the sample, maybe this is a noise because for a lot of people, if you have the weight increase in the first year lower than 2.5, that's already bad. So the idea for this one is after doing some statistic on the entropy of that branch, the green color, you will reduce the tree by cutting the whole thing and make it into a single set, and that decision is bad. This kind of idea is very popular. We do that all day because you don't have to make the exact decision right here, but just a little bit is here somehow you think that some error is enough. I don't need to make a perfect system, right? Because there's noise in my data, and I will consider that decision good is a noise. Okay. Well, there is another way of making the tree better by raising the tree. Well, subtree raising goes like this, as you can see. There are some lift, one, two, three, four, five, like this one, right? But when you do from the bottom up, what you see is that the set one, two, three consists a lot of samples. So the set in the C tree, they consist a lot of sample compared to node 4 and 5. If that is the case, then the sample in class 4 and 5 will be considered as noise. Think about it. If the branch of C has about 1,000 sample, 4 has only 3 sample, and 5 has only 5 sample, for example, then they are really small compared to 1,000. So the wise decision here is that I don't need to check B. I will ignore that branch of B, and then I will distribute sample in 4 and 5 into 1, 2, 3 based on the attribute C. And that make my tree look simpler. And yes, I accept some sort of error when I classify, but maybe that's not error. Maybe it just, you know, um, is somehow a way to generalize things because there's noise in your data and you just consider that to be noise. Okay, that's how you raise the tree up, cut out some node if unnecessary, or the volume of that node is too small. Okay, that's the idea. Now, we are talking about something called error rate in decision tree. And in many cases, you need to consider this error rate during the construction of the tree. Okay, so the basic principle here is that you only cut the tree when that cutting does not increase the estimated error. Well, that's kind of hard. And remember, every time you cut the tree, you have to re-evaluate the error, right? And that's a little bit painful because saying about it, you have like millions of sample in your data, and you have to measure the error rate for some data, testing data, even 10,000 of testing data is huge. But there's no other way. Okay, we have to deal with that. Now, as you can see, we can reduce the error while running the tree using some techniques. And here, what you see is that we can consider a tree with, let's see, what I have here. It has been a while. I didn't really read those kind of text because this slide, when I prepare it, is very worried. I really want to update this one. Okay, so the idea of reduce the error of running is that you will split your data into a growing and running set. So you have two sets of your data. Your training data will be split into two parts. Okay, one data is only used for growing, and the other data is used for pruning. When you make the tree, you use the training data for growing only, and when you're pruning the tree, you use another data set for pruning. That's the idea. But I not really agree with that idea. I feel like this one is not a good way to do, even though they suggest it. In practice, no one do that. Okay, they just feed the data into decision tree and let it run. So I don't think this kind of node is very handy in practice. Well, there are some other thing about decision tree that you may find on the internet, like decision list and decision graph, which I believe very rare. You don't see it very often in practice. And there are some note on rules and trees. Well, rules is just like if A and B and C, then do D if something something. All of that are rules. And decision tree is just a collection of rules. So you may want to provide a decision tree for user, or you may give a long list of rules for user to make decisions. That's your choice. Well, I don't think this give you any insight about decision tree at all. Another application of the decision tree that you may encounter is the regression problems. Well, you know so well about regression, I believe. That's the problem of predicting the output y given the input x, right? And you may modeling your data in a linear fashion. Well, in other words, y has a linear dependency with s, right? And you can do so if you want to. Or maybe y and x has a non-linear dependency. That's your choice. But anyway, for decision tree, this is very tough. Is the decision tree is not designed for these regression problems. But if you have to make decisions tree for this regression problem, what can you do? The trick is that you are going to discretize your y into several sections, and then you can consider that regression problem just like the classification problems. Okay, you discretize y into bin, and those bin will be the class you will classify, right? You can do so, but I don't recommend doing that. It's very bad idea. But some people still do that. I don't know, nowadays no one do regression using decision tree, but maybe still some people preferring that. And if you want to predict the value in uh, fine a very fine scale, then you need to discretize a lot. There are so many classes to classify, and your problems turn out to be over 15 problems, I believe. So be careful with that. And finally, let's see. There's some difference between the decision tree with the classification tree. Well, these are just some notes I made based on the regression problem, so you may want to read it later. And yeah, that's something you need to know about decision tree. And before we move on to the next lecture, I think we will talk about some sort of demo. So let me have a demo for decision tree. Wait a minute. Okay, so let me share with you this one, and let's talk about it. Okay, so as you see, this is a demo of random forest, and I'm going to give you some demonstration here. Well, let's say this is a famous guy that a lot of people knows. And you know Kabathi, right? He's a very famous guy in this field, if you will. Now, what you are seeing is a demo of the random forest, and I believe that we are going to talk about random forest later. But right now, let me have one single decision tree only, and there are some other option you have to choose, like the max depth of your tree. So if you make your tree to be very deep, then you can have the accuracy to be 100% for sure. Okay, and the number of hypotheses per node. Well, this is another issues that you may want to check out later. Right now, I don't care about this one because it's only applied for random forest anyway. So let's take a look at your data. Your data now is a bunch of data point in 2Ds, right? X and Y. And now you have to classify them into two class, either green or red. And if you allow your decision tree to go very deep, then the classification error will be zero. There's no error at all. You have 100% accuracy here. But then if you change your decision tree a little bit, you cut the tree, okay, you make the max dip a little bit, let make this tree short, then you can still, for some reason, obtain the same performance. But what if I have the max depth to be 3? It's still good, right? It's still good. But of course, 1 is not good enough. So I may add some data point here for you to see. I would like to cover the green blocks. Okay. And all right, this is odd because now if the depth of your tree is only 2, given this kind of data, it's very hard for the decision tree to make a good decision. Therefore, what you are saying is that it's favor the green color because now looks like I'd rather make some wrong decision on the red data than make a wrong decision on green data because the green data is massive, you know. And because of that, I may want to increase the depth of my decision tree a little bit. And as you see, just by increasing the depth of my tree, now looks like my decision tree can classify a little bit better. Of course, there are some error in the green and red area, as you can see here, but it's not too bad. And if I keep increasing the depth of the tree, I can get even more accurate classification result. Okay, and this is because you are having overfitting problems. Okay, so you don't want that, and that is why people try to avoid that by having another algorithms called random forest. Now, for random forest, you can have a lot of tree rather than just one tree. Let's say I have hundred of trees, like you have hundred of people to make decisions, and each one may make different decisions. Okay, so how to do that? For random forest, there's very nice algorithms, as you see. When you select an attribute A, you have to compute the gain of attribute A over the set S. And if you have like thousand of attribute, what happens? If you have 1,000 of attribute, then that means you have to compute that gain 1,000 times, and that costly, right? It costs you a lot. So you don't want to do so. What you want is to make your computation process a little bit shorter than normal. Just to select one attribute and you have to compute over every attribute, that's make no sense. So in decision tree, what you do is you randomly pick some attribute. Let's say I have 1,000 of attribute, but in order to select an attribute A, I will pick the best attribute among k random attribute. In other words, I pick randomly, randomly 10 attribute, and then I will select the best attribute among that 10. Okay, and then I keep growing the tree that way, and I will have one tree. So think about it. You may have like thousand of tree, and each tree will grow differently. They will be the unique one. You cannot find two identical decision tree if you make the tree that way, and that is good because we are making diversity in decision tree. And when you try to make decisions, you will compare your decisions based on hundred, no, thousand of decisions, like this one. And as you can see, if I apply that principle for random forest, you will have very smooth decision barrier like this one. It's nice, right? And you can see that even if I reduce the depth of my decision tree, still the performance does not reduce a lot. And even if I increase the depth of my tree a little bit, my tree not really overfitted, right? It still somehow fit with my data and allow some sort of error in the middle. Controlling it this way. So that's about decision tree, and that is why we care a lot about decision tree. Okay. Now, one thing that I believe some of you may know, or you may not, have you ever Kinect camera before? Any of you? Raise your hand if if you know about that Kinect camera. Let me see. Is any of you trying to use Kinect camera before and having some idea about how it works? No. That's really surprising because I think you have a chance to approach those technology better than me. Anyway, let me give you a hint on this one. And this is really, really interesting. So, what can I show you? What can this is? Let's see. Okay, I have it in page 44. Well done. All right. Can you see my screen? Yep. So this is um, a technical report provided by Microsoft, and it's very long report. Just give you a lot of insight about how to use random forest for different problems, and one particular problem is apply is this one. Okay, what you are saying is that they apply the decision tree in order to detect human John from the depth image captured by the camera. So Kinect camera is the camera that allow you to measure the distance between the object with the camera, and that's applied for several games in general. And this is really interesting when you see that instead of using some deterministic algorithms, they use machine learning here using random forest and training the classification of human tone based on, and the accuracy is really cool, as you see here. Okay, this is the classification for us in Kinect for Xbox. I didn't happen to buy this one, but I have this one. I have Kinect myself. So that camera and the software goes along very well. We can really have detection of human tone very accurate, and we play games with that by just swing your body around, and you don't have to worry or wearing any kind of device on your hand, and that's a good thing. Okay, you can read more about this applications in the document if you want to, but that's a study case. There are some other thing about regression for us, and some other problems in medical image processing too. If you scroll down, you will find some other interesting applications. It's very depend a lot on the problem itself. Some problem is hard to understand. Some is very easy to understand. So this one is for estimating the density of the data. Okay. Some problems in data science, but hopefully you can grab some idea from this report, because it's really nice, I believe. So have fun with that. Okay. Now let's we move on to another topics, which I believe some of you very familiar with. We are going to talk about Bayesian learning. Let's see. Oops, words. No, 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 no. Let me see. It's close. Okay. Hold on. Um, okay. Let me share it again. Okay, so some of you may be very familiar with Bayesian learning, and Now we are going to talk about it in machine learning, and let's see if we can get some good idea from these topics. So we will talk about linear predictions as well as Bayesian learning today, very quickly, I suppose. So first of all, let's talk about linear prediction. What is this? And you encounter this one very often in practice. What we see is that a lot of process, a lot of problems in predictions. Okay, and that's normal, right? We use that all the time. And for some reason, the linear modeling tools is very important because it gives you the solution analytically. That's a good thing. But in some other cases, this is not enough, and we have to find a better way, like nonlinear modeling for our data. So right now, let's just put that aside and observe some sort of example. Now, what you see is that we have data, right? Data collected from a building. They have some device outside to measure those, and they count the number of people inside the building, and they also measure the energy requirement according to that. And as you can see, the given that information, you will predict energy requirement for this one. Models like y equal is going to be the parameters that you have to estimate, and b also another variable, but often we call this bias. Okay, and you are trying to minimize the error between your prediction and the ground truth. The ground truth is your observation over here. Okay, that's what happens in our setting. And given that, you can see that people apply this linear prediction in a lot of applications. This particular data is the data provided by US government. So they measure, they collect the data, they 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 try to let's say they try to find the relationship between the poverty and the birth rate of teen. Well, looks like looks like there's some sort of relationship, as you see, and it's hard to say it's just linear, but let's just assume that there's a linear relationship between the birth rate, the teen birth rate, and the poverty. Then you can try to minimize the error in this predictions by using a linear model. In short, you are having in short you are having a straight line on this graph to measure the thing. Okay. There is another data that you may find in U.S. Government website. They open that data for people to see. Those data is the size of lung in children from 6 to 10 years old. Well, you can see that for each age, the lung size may distribute it differently, but the mean is somewhere along the line you are seeing. So that is why using linear models still give you some informations, and not too bad, right? You can also see another observation here. Looks like they gather. more and more information. And in this case, up to this time, the observation is still good. Of course, if you are over 15 years old, maybe the data is unavailable or just it's no longer grow that way. And up to some age, your lungs no longer expand, and for that, the linear assumption no longer works. This is why we only observe the data in some period from 6 years old to 10 years old. That's the thing. Well, oh, I think I should clean up my my slide. I'm sorry, I used that slide a lot of time, but hopefully you can get what I'm trying to say. Okay, let me clear a little bit of thing here, and let's see what you have. All right. So the linear model can be expressed as you can see in the formula: y hat equal to x ij multiplied with theta j, where theta j is going to be the parameters that you are observing. Well, what is yi? Yi is the label. Oh no, yi is the label of the data sample I. So the index I you are seeing is actually represent the index of the sample, okay? And the index j is the index of the data field. So for example, your data has d dimension, then j will be from 1 to d, okay? So if you write this one into a vector formulations, what you see is that xi here is a vector of d value. Okay, from here to here is a vector of d value, and theta is also a vector of d value. Okay, and now yi equal to theta multiply what x 1 to xd. Is that? No, it's not that. It's not that. What you're seeing is not really this way. Okay. Oh, you have x10 to x1 d. Okay, and here you have theta 1 up to theta d. And as you multiply, you will have y1. Okay, and that keep going until x10 up to x and d. Okay, and that's the um, vector you need. I should clean this one. It's too messy. I did something wrong here. Anyway, all right. This is easier for people to understand. Now you have x is the data, y is the data, the label of the data, and theta is the parameters you have to estimate. And how do we estimate? You get the y hat and x. What do you want to do here? You want to measure theta as the argument means of the loss function. Well, how do we define the loss? It depends a lot on your definitions. You may choose the mean square error or something else. That's your choice. Okay. Then, given that, I think you can form the very first and very popular mm, loss function here. Jacobian. Many times they call it Jacobian. It's the square error. The error transpose multiply with the error again. This is the square root. Oh no, no, just square estimate. This square estimate of the Jacobian. Okay, so this is how we have. This is how we have theta estimate from this one, where y hat is the predict predicted label, and y is the label itself. Okay, and that's all about linear prediction. I think we will talk about it later, not now. It's just so simple. No one wants to talk about it here. If you want to optimize this Jacobian, all you have to do is calculate the derivative of Jacobian subject to theta, and you can easily get a closed form solution. So we are not going to talk about it here in detail. That's unnecessary. Now we should talk about Bayesian learning because this one is maybe the most popular learning techniques that people use, and it's based on probability. Okay, so let's go. Um, yes, it's involved some probability manipulations. So you have to understand some basic of probability, and I believe all of you did, right? And all the optimization process can be made from probabilities. Very simple. So they say that Bayesian learning are the learning algorithms that most practical approach in machine learning world. Before you enter the area of in the realm of deep learning, people keep using Bayesian learning a lot. I mean, a lot because it's very practical. All you have is data, and all you have to do is just let's say doing some counting and measure the probability of this thing and that thing. That's easy. The more data you have, the more accurate estimation of probability you have. So people use Bayesian learning a lot in practice, and until one day the deep learning and neural network becomes something dominant in the world. But the deep, uh, well, what can I say? Um, Behind the scenes mechanism of deep learning is just nothing but statistic. In other words, whatever you do, may your deep learning models solve the problem very well, but that is because the inside of black box, inside of that black box, is learn the distribution of your data, but you cannot express it explicitly. Okay. Now, let's say that we can have some discussion on Bayesian learning because this one is also a very simple topics. A lot of you may already know it, right? Okay. So in Bayesian learning, we say that each training sample will incrementally increase or decrease the estimation of a probability. Okay, that makes sense because if you have more data, the estimation is more accurate. Okay, so the probability you just had before can increase or decrease based on some new sample. That's the first thing. The second thing is about the prior knowledge. So sometimes the prior knowledge can be integrated into the process of calculations, and we use that a lot also, right? And well, let's see. I think we should jump into some example and see what happens. Well, here we go. I think that, yeah, I think I can discuss this one now. Do we need to repeat that one because this one is so basic? This is the Bayes rules, the probability of hypothesis given the data is nothing but equal to the probability of data given hypothesis multiplied with the probability of hypothesis and divide by the probability of the data. Well, the probability of data is something you can gather from your data, right? Yeah, but that's just in theory. It's not real. We cannot get the exact number of PD. No way. PH, the probability of the hypothesis, that actually the prior. You need that prior in the estimation. And one term that you may have a look, and that is the one I'm pointing to. I call it likelihood. It's actually the distribution of data given the hypothesis. For example, if you are measuring the number of people who got disease and number of people who doesn't have disease, and D is some sort of measurement you have in the how Jacob sheet, then the distribution of D given six is something you see on the left, this line, okay? Looks like people who really got sick will mostly have the measurement of their health somewhere here. And for some people who doesn't have sickness, they have their measurements somewhere here. And it's all about probability. It means even if you don't have any health issues, still you can get some result here, some measurement here. Who knows? And that's very low chance of observing. Why for some people with the sickness, sometimes you will observe their measurement here, their numbers here, like they are normal people. So normal people can be sick too, right? So that's the whole idea. You may have mm, this as a reference for our problems later. We will talk about it in detail for some uh, particular problems, but not now, not yet. Okay. And so in Bayesian estimations, many times, you are looking for a hypothesis that can maximize the probability of hypothesis given the data. That's what we call maximum a posteriori hypothesis, or MAP. And you see this one a lot in the textbook as well as in some other applications. They keep talking about using MAP for classification. Well, MAP is nothing but a way to find the hypothesis based on this mechanism. Okay, maximize the a posteriori, and that probability PH given data, P of hypothesis given data is, it can be written to P data given hypothesis multiplied with P hypothesis divided by P data. But now, because you are maximizing over the hypothesis, therefore you don't need to care about the probability of the data. Okay. And if you don't care about the probability of data, argument max over the whole term now can be reduced to the argument max over the thick sorry the product of PD given H multiplied with pH, and of course pH, the prior, is not a uniform distribution over H. If you have that one, then we can easily calculate everything we need. You have the likelihood, right? The likelihood is P of D given the hypothesis H, okay? And if you know nothing about the hypothesis, if you know nothing about the hypothesis, the probability of the hypothesis it is equal for every hypothesis. In that case, the hypothesis will be the one that maximize the probability of data given the hypothesis. And in that case, you have another estimation called maximum likelihood estimation, or you have one thing we call MLE. Okay, this is exactly what I just mentioned. And let's play around with one particular example. Well, you know that there is 0.8% of people in this world got cancer. Okay, and this one is kind of uh, a truth, right? There's no argument. Just say, I know it. That's the fact. You don't argue with me on that. Okay, so that's fine. I'm okay with that. And now you can write it into some sort of prior. P of cancer equal to 0.008. Okay, so that's the probability of someone getting cancer. Now, this is a problem that we use for predicting if you have cancer or not. So what you see is that you go to the hospital, they measure your health, and after checkup, they say, okay, you got cancer. So they say 90%, oh sorry, 98% of patients are correctly classified as positive. Now, tell me, what is that probability? With 90% of patients are correctly classified as positive, what is that probability? What is the probability they are mentioned? Can you give me some answer? Anyone? Just type on the chat box if you feel comfortable. Okay, thank you. Yeah, my question is, what is the probability that the sentence mentioned? So one of your friends just type it on the chat box. The probability of positive given cancer is 0.98. Okay, looks like you got the idea. So I just put it here for you guys. Probability of you receive a positive when you got cancer is 0.98, and hope that this is the correct answer. Okay, remember this is very important. Now we have another statement. Say 97% of patients are correctly classified as negative. What is that probability? Can you tell? Okay, looks good. So now you have the probability of negative given no cancer. Okay, looks like you have very consistent answer. So probability of negative given no cancer is 0.97. Okay, thank you. So this is what we need. So I did make some calculation here, but in case you want to check it again, just do it. All right. So we have the probability of cancer is 0.8%, and yeah, it's unlikely that you have the probability here because that's not what we have. Okay, probability of observing positive even cancer. That's what we are mentioned. And also the second one give below. So what we care is that will you have cancer or not given a positive uh, checkout. So if someone give you a, a test and they say, okay, you are positive to cancer, do you really have cancer? Given the fact that we are using Bayes, you can easily write that the probability of cancer given a positive check equal to the probability of that positive check multiplied with the prior of cancer divided by the probability of the positive, or may you say the probability of positive will be the probability of positive given cancer. This is the John probability. This is the probability of positive given no cancer. This is also a John probability. Sum them up and you will have what we need. So if you take some time and replace the numbers, you will have 0.98 multiplied with the probability of the cancer is 0.08 divided by the probability you have over there, 98% multiplied with the probability of cancer, and only 3% multiplied with the probability of no cancer, and that gives you a number here. Okay, so the probability of cancer given positive is only 0.2085. What about the probability of no cancer given positive? Can you calculate this number? What is that value? What is that value? Just do the math. No, you have to calculate that. Is that, are you sure? I'm just asking. So basically, in form of logic, you can easily get this one to be one subtract to 20%. But can you verify it by calculating that number again using the Bayes formula? You come and do the math again. I suppose that you end with the final conclusion that you get the still have a high chance. That's what they say. So yeah, this indicates a thing because that you more can get your house rather than trust when it give you a lot of cancer. It's necessary to have still alongside of humans around. There's only 8% can have cancer. So stay healthy and yeah, try to be more careful with your health anyway. But yes, say okay. And what material you can find some other note that are provided about maximum posteriori hypothesis (MAP). You can use this tool for estimating some sort of functions. And in the end, you see that well, the probability of getting cancer and the probability of getting no cancer is very different. So, in the end, the probability of having cancer, even positive, is very low. Okay, I will end up with the conclusion here. This is the probability of having cancer given positive test, and this is the probability of having no cancer given the positive test. It's not 1 minus another. as you suggest, even though I understand your logic. You mentioned it and it's correct, but it's not true. There are so many things that we need to consider, and the probability of cancer and no cancer given positive is not exactly that. Okay, so you may want to check that one later in the material. All right. When you deal with problems, there is a questions that we need to ask. What is the most probable hypothesis given the training data? And what is the most probable classification of a new instant? Well, why this question are very normal? It poses a lot of concern. Why did they ask that kind of questions, right? So take a look. Um, what is a hypothesis? Well, think about hypothesis as some sort of assumptions, or maybe you can think about hypothesis as a classifier. So given that what you're seeing is that in this example, I have three classifier representing by hypothesis H1, H2, and H3. There is a posterior probability of hypothesis saying that, okay, the probability of the first classifier is the H, the hypothesis getting from MAP, and there are 30% of chance that H2 is HMAP, and there is also 30% of chance that H3 is HMAP. So you have three hypotheses with different posterior probability. Okay, and given a new instant, it is classified positive by H1 and negative by H2 and H3. The question here is, who will you trust? Will you trust that H? Will you trust H1, or will you trust H2 and H3? Normally, your logic will tell you that you should trust H2 and H3 because two people say negative and one say positive, right? That's what happens. But when you do Bayesian learning, it's not that way. Okay, so we tend to find the class that maximize the class given the hypothesis. Is that right? Probably. Okay, so the probability of a class C would be the sum of probability of the class C given the hypothesis I multiplied with the probability of HI. And given that, you will see we can have different explanation here. Okay. Well, it depends a lot on your calculation. So be careful. We need to calculate the probability of positive or negative here. Okay. You need the probability of the class given the hypothesis. Uh, more than 50% in general. All right. So putting all together, you will this kind of formula. What do you have is that the class C is the class that can maximize the probability of the class given the data. Using the Bayesians, you can see that we will take over every possible hypothesis or every possible models or every possible what classifier, whatever you call it, that's fine to me. Okay, so think about hypothesis here in this context as a models or a classifier or whatever you want to call. Okay, So it's the class that can maximize the sum of probability of the class given the hypothesis multiply with probability of the hypothesis given the data. Okay, and this one is really annoying, but we can deal with that. Now, let's look at an example. You have some sort of tabular data like this one. This is tabular data. You have six attributes: sky, air temperature, humidity, wind, water, and forecast. Okay, and you will have to make decision either go to enjoy the sport or not. Okay, so for the first test data, the example number 7, what you see is that you can easily make the decision yes, because yeah, it's identically equal to the very first example, I believe. So that is a decision. But what about 8? You couldn't find it in the example. So how do we do that? Well, in that case, you have to make some assumptions. Well, we say that because the number of data you collect is very limited, so there's no way you can, uh, let's say, have the probability of data given this information. You only have 6 samples. How do you calculate the probability of the data given hypothesis or given the class? No way, right? So, uh, if that is the case, then what can we do? We say that let's assume that all the attributes you have in your data are independent from the class. Well, in other words, we have a concept called conditionally independence. We say that all of these attributes are conditionally independent. You are saying that property of A1, A2, AN given the class C is equal to the probability of AI given probability of AI given class C. So this is what we call conditionally independent. Independence. Okay, those attributes are not correlated to each other, even though we know there are some correlation between the attribute and the class together. But then in nature this very your now given that can we derive property of sky equals sunny given the class? Yes, it will be. Can you count? So we have sunny and sunny and sunny, and yeah, I would have what? 3 over 4, 75%. Okay, so before that, maybe we have no way to calculate the probability, but now we can. So I can literally compute the probability for you in form of a table. It requires a lot of care when we calculate things, but yeah, I can write it down here. For sky, we have three probability, right? Sunny, rainy, and cloudy. So for yes and no, yes is 3/4, and for rainy, no, we have cloudy, no, 1/4. And for no, we have only two sample. So you have rainy one and sunny one. Okay, so 1/2, 1/2, and 0. Okay, so you have all the information you need, and given that you have all the class you want, and you can do the same for air temperature. So suppose that you are concerning about temperature, you have warm and cold only. So you have warm and cold, yes and no. For yes, warm will be, oh, 100%, right? And for no, we have 100%. And it keep going, right? We can do that all the time. So let me say high, normal, and low. This is yes, this is no. So for high, what is the number we have here? One, two, three, 3/4. And this one gives you, how about normal? 1/4, right? And 0. How about no? In case of no, you have high and high. So this is 1, this is 0, 0. It's kind of weird. And what about wind? You have strong and weak, yes and no. So for strong, for yes, you have strong, strong, weak. Also 4, 3/4, and 1/4. For no, what do you have? One strong and one weak, so 1/2 and 1/2. So for water, you have warm and cold, yes and no. So for yes, you have let's say warm, cold, cold. So 1/2, 1/2. For no, you have warm and cold, 1/2, 1/2. That's odd, right? Chain and the same, yes and no. So here we go. Same. Yeah. Okay. 3/4, 1/4. And for no, you have 1/2 and 1/2. So everything is ready. Okay. So can I calculate the probability of the sample A given the class? Yes, I can, right? Probability of the data A given the class? Yes, it should be the product of all the number you have. So I have sunny multi sorry multiply with warm, multiply with low. Oh, what do you say? This is 0. I no longer care because it's 0. Now I am interested in compute the probability of observing dA given no. What should I have? I will take another color. Let's say sunny and warm. Oh dear. So you get 0. See? So this is really trouble. If you employ neighbor, yes, you can calculate all the probability you want. But the issue is, up to this moment, what you see is you cannot make decisions because when you play sport, the probability of observing this sequence of attribute is none. And also, when you do not play sport, the probability of observing this data is none, zero. So in the end, you cannot make decisions, right? So this poses a big deal in neighbors. Sometimes you don't have enough data for calculating, and there are some issues as you may indicate here. There are some special cases where your probability is zero, and because we are going to deal with the multiplication of probability, so you don't want this zero number appear in the product of probability. No way. What we do, we will try to find a way. Okay, and there are some tips for doing this. uh, Here we go. Let's see. I will skip a little bit of detail here because you guys may not need it. So just take it and read it at home. I think this is very easy. So I can skip this one. Maybe I will end up with some calculation. Here is the detailed calculations, just like I did before, but in a different way. Anyway, what we are trying to say is, what if the fraction is too small or is zero? If that is the case, then there's no way you can compute the probability, right? So the idea here is you should introduce some sort of data, auxiliary data or additional data. So let's say I'm going to put m sample of data into my original data set. In original data, you may have n sample. Now I decided to put into my data a few sample, m sample, and then I now can literally smooth my probability using this formula. So for example, the probability of the sky equals sunny given the blast, yes. Uh, Earlier it will be 3 over 4, right? Because I have 4 sample of data and I have uh, three sample with the sky property equals sunny. So you get 3 and 4 over here. That's fine. And then I will inject to my data one sample. So m equal 1. Okay. And the probability of sunny is 1/3 because you have three attributes, right? Sunny, rainy, and cloudy. So the probability of sunny is 1/3. That is p. P is 1/3. So you can easily compute the probability now is 10 over 15. That would be a little bit different from the probability you had before. But this one better because if you compute the probability of the sky equal rainy, given the decision is yes, that will be 0 plus 1/3 over 4 plus 1. It should be 1 over 15. This number obviously differ from 0. And if it is differ from 0, when you multiply the probability, you will have a small number but not 0. And in the end, you will, for some reason, be able to make decision. Okay, your probability will not reduce to 0. And that's a good thing about this technique. We call this uh, probability smoothing. Okay, so hope that you can use this in practice. And there are some other issues related to neighbor-yes classifier that I think that you guys can read it later. Just to tell you one thing, long time ago, when we don't have deep learning, people still use Bayesian learning for some classical problems like text classification. And in text classifications, they mostly use for spam mail classifier. Thing about it, they collect a lot of email and they classify your mail into the spam mail and normal mail. And so based on the probability of your data, they can make decision. But at the moment, we don't have any deep learning models like that. So the only thing that available in their hand is statistic. So what they did is they used neighbors for classifying the email. They measure the frequency of occurrence of every possible word in your email, and then assuming that those words are conditionally independent from the class, either spam or not spam, and then using neighbors, they will classify it. And this is a very classic approach that we have in neighbors for text classification problems. Nowadays no longer being used because our nature language is so complicated. It cannot be modeling using this neighbors anymore. Okay, long time ago we used this because we have no other way. But nowadays we should approach the problem using some other techniques. So maybe we will have a talk on text classification using deep learning later. Okay, so that's it. That's what I want to share with you today. And sorry that I still didn't clean my material. I should clean it before teaching you guys. I'm sorry, I'm too busy for that. But next time I will be more careful. So thank you for your attention today, and I will see you next time. Okay, see you.
Teacher,
Yep.
I have a little bit confused about the conditional probability.
Yes,
Can you turn back to the slide say 17?
17.
Yes.
Which one? Oh, okay, 17. This one?
Yes. I
Okay.
uh, In the line number three, I see that's the probability of non-Bayesian given the non-cancer is 0.97. So
Yeah.
and the probability of patient given non-cancer is 1 minus 97%. But in the number line number 4 and 5, we don't
Hmm.
it's like that. So can you tell me the difference and how to distinguish between them?
Okay. So it goes like this. You have the probability of cancer given a positive test is equal to the probability of a positive test given you have cancer multiplied with probability of cancer divided by probability of positive test. Okay, and because you don't have any idea about this probability, so do I care about it? Maybe not. So I can ignore that. This is why we didn't use the equal sign here, but we use the approximate, because you don't know the probability of the positive test. It just appear there in the bottom. So if you have to divide the whole thing by some constant, then do we need to worry about that factor? No. So if I have to compare the probability of cancer given positive with the probability of cancer given, oh, sorry, the probability of no cancer given positive, I also have this probability of positive given no cancer multiplied with probability of no cancer divided by probability of positive. Now, if I have to compare these two, what should I do? I I either divide the first one and the second one, or doing something with that, whatever the case, I don't mind. But the important thing is this value and this value. So I don't really care about the second term. This is why we use the approximate sign here. We
Uh,
don't care about the other side.
so we eliminate the property of Python. I thought that we should compare the right ratio between the two property. Uh,
Yeah, yeah.
yeah, yes, yes.
I'm sorry.
And
Maybe I made a mistake when I explained to you. You were right. I know what you mean. Last time you
yes,
say probability of the cancer given positive equal to um, the probability of, no, sorry, of one subtract by probability of non-cancer, right?
yes,
Make sense?
yes.
Okay. So let's see. If this is true, if this is true, then what do you think? Can we verify it for some reason? I just want to verify it. Now, can you calculate the probability of positive? Now, do this for me. Calculate this number. What is it?
Calculate the probability of non-cancer
P
given
positive. No, this is
uh,
the probability of having positive. This is P positive.
P positive. Yes. Wait
What's
a
that?
minute. Wait.
Can you give a number?
Can you? That is 0.0
Zero point
3
three seven
7
six.
6. Yes.
Okay, thank you. So if that is the case, then let's say, can you verify it by dividing this one to 0.0376? What do you have here? And if you divide this one to 0.0376, what do you have here?
The, the line number 4 is equal 0 point 0 point 2
0.2.
2 0
Okay.
uh,
Zero
and
8.
7. Yes. Approximately.
Okay. And the second line,
Second line is 0 point 792.
79. Okay. Two. Okay, so you got your answer. You're actually correct. You
Yes.
didn't wrong. You didn't do anything wrong. You are correct.
So
The thing confused about the number because in the material I try to simplify thing. I say there is no need for calculating the probability of positive. Okay,
yes,
in,
yes.
in in general you have to calculate that one in order to give the correct number of probability of cancer given positive test. But here I don't need that because as you can see there's no reason to do so. But you were right. We can always confirm that formula. This is the correct one. So we clear, right?
Oh, yes, yes.
Okay.
Because in the previous slide, you told me to calculate the property of given. So I thought that we can calculate by using one subject the the non the
You're
yes,
right.
yes,
You're right. We can just take one and subtract with the other probability, but
yes,
for some people, it may not convince. You know,
yes,
it may
yes.
not so convince.
Yes, I know you. I did. Yeah, it's a good issue. I just
Yeah.
want to confirm.
Okay. All right. So everyone on the same page, and thank you for your reminder. I know that this is a little bit confused when I show the old material with the one I'm talking to you. So next time I will clean up the material first and have a clearer explanation. I'm sorry for today because I just have some other meeting before the class. But anyway, thank you for your attention. I'm glad that you asked me some questions and clarify what I just said. So thank you so much, and I will see you next time. We will talk about some other topics next. Okay. So yeah, I will upload the slide to you to the PCal. Don't worry, I will. Okay. See you guys later. Thank you. Yep. Goodbye, everyone.